And our last speaker before the Flash Talks is Naomi Coombes from UK Health Security Agency.
Hi everyone, so I'm Naomi Coombes, I'm from the UK Health Security Agency, and I'm going to talk to you today about the work we've been doing with human alveolar models with infecting with pathogens of pandemic potential and assessing medical countermeasures. So for any of those who aren't familiar with what I mean when I'm talking about microphysiological systems, this encompasses a spectrum of technologies which we can use to recreate the structure and function of organs in a controlled in vitro setting. And it can encompass anything from things like bioprinting, spheroids, organoids. But what I'm mainly going to talk today to you about is organ-on-chip technologies. And so these technologies are part of a kind of movement globally to move away from animal testing. And a lot of the regulators are supporting this now. So, for example, the FDA is on their third Modernisation Act, supporting the phasing out of animal testing. The EMA and the NIH have both set up task forces to help the regulatory acceptance of these technologies. And they're already being used to support clinical trials. So we wanted to use these systems to model infectious diseases caused by pathogens of pandemic potential, and then use them to look at preclinical evaluation of medical countermeasures. So the system that we are using in our lab is predominantly the commercial system generated by Emulate. So for those who aren't familiar with that, we've got the two bits of like large hardware which drive it. So the orb is connected to the gas and the power, and that provides the gas and power to the Zoe, which sits within the incubator. So the Zoe is what actually controls the conditions that the chips are cultured in. So it controls the flow, the gas, the stretch. So the chips themselves are these small kind of PDMS structures which contain two cellular channels separated by a porous membrane, and they sit within these pods which house the media and the effluent. So on the right here, I've just got a kind of cross section of what we're looking at in the chips. So you've got two channels, as I say, separated by a porous membrane. On the upper channel, we culture the epithelial cells of our organ of interest. On the bottom, you can culture the endothelial cells of the vascular channel. And either side of the channel running parallel to it, we've got these vacuum channels. And this allows the machine to add the biomechanical stresses that the organs experience in vivo. So for lungs, this would be breathing or peristalsis in the gut. So we can recreate these really quite structured human organs in vitro. So we work with these at high containment. So I'm sure you can imagine that containing these systems can be quite challenging. They do create small aerosols, so it does all have to be contained. So we had a flexible film isolator custom built for us, where we can house a full-size incubator with all the equipment needed to run it, and also the microscopes all within containment. So everything can be done within containment before it's inactivated and brought out at the very end. So you can see here we can kind of pop up in the middle and work with everything in this big plastic isolator. So the first thing we wanted to do with the human organ chips is we want to compare the two systems that Emulate have set up. So they have an alveolar and an airway model. So we wanted to compare the SARS-CoV-2 infection in these two models to see which we would take forward for further use. So the alveolar model, as you can see, had a much more robust infection. But also what I haven't mentioned is the alveolar model is a more complex model, as this model contains endothelial cells and the stretch, which mimics the breathing, whereas the airway model is just the monoculture and you don't require the stretch for breathing. So we took the alveolar model forward for further testing. As I say, we've got a more robust infection, so we'll be able to look at knockdown by medical countermeasures, but also by representing a more severe disease state, we're able to look at more severe disease states in the deep lung. So we took forward the alveolar model for coronavirus infection studies. So the top panel here is the same image as I showed on the previous slide, but we've also now added in SARS-CoV and MERS. And we can see that over time we get a really nice robust infection with all of these pandemic coronaviruses. So we're satisfied that we've got a nice model that we can model human coronavirus infections. For example, like MERS has been traditionally quite challenging to study in animals. So by having human relevant models, we're much better prepared for the next pandemic. And actually, MERS was we had the most robust infection with the MERS infection, and was the only one where we actually saw high levels of shedding into the endothelial channel. So once we were satisfied with the model, we wanted to start looking at medical countermeasures. So to do this, we first do a screen in a more simple transwell system. So the chips I've been talking about today, they're quite expensive. They're about £1,000 a chip before you even start putting cells or media in them. So we want to do an initial screen in transwells to just get the dose right and make sure that we're going in with an appropriate dose into the more expensive chip system. So the drugs we screen today are the EID 1931, which is the active metabolite of molnupiravir, the nirmatrelvir, which, as someone mentioned earlier, is the active component of Paxlovid, and also Tylerone, which is an interferon inducer developed in Russia. But Tylerone was shown to be toxic at all concentrations, so not taken forward. But the one I've shown here, just as a demonstration of what we do in a screening test, is we tested up to 100 micromolar of the drug, with or without MERS. I've just shown with the MERS at the moment. And we can see that at the lower concentrations, we weren't getting inhibition. At the high concentrations, we weren't getting virus, but we're also getting the toxic effects of the drug. So, for example, for this one, we decided to go into our chip infection with 1 micromolar. So once we've done our screening in the transwells, we move on to the more complex chip system. And so far, we've put EID 931 in with SARS-CoV-2 and nirmatrelvir in with MERS. And on the left of both of these panels, you can see where they're infected and treated. And in both of those, we saw no virus replication, but in the untreated, we're still seeing this robust infection. So we're satisfied that we've now got a nice model that we can model pandemic coronaviruses and potential inhibition by medical countermeasures. So the work I've spoken about today has all been on human chips, but I just wanted to touch on briefly some of the work we're doing with non-human primates. So non-human primate organ chips are seen by the regulators as a way to kind of bridge the gap between the legacy data that's already existing for animal models and these new human systems to take forward. So we're able to take advantage of the primate colonies we have at UK-ICN, and we use the natural turnover of these to isolate cells from the organs of interest as animals become available. So we've discovered that it's been more successful if we generate organoids from these tissues, as not only do we get longer term viability and expansion, but we also retain some of the tissue, the kind of complex tissue architecture from the organs of interest. So far, we've attempted to do alveolar, airway, and gut. Our airway and gut have been successful, but alveolar has been more challenging. And said here, we do have them culturing on chips successfully. Unfortunately, the guts have now failed. At the time of writing, they were doing quite well, but the airways are still doing well. So hopefully, we'll take those into doing coronavirus infections compared to our human chip models. And then on the left here, I've just got some representative images of some of the so we've got the top left, we've got some EM images we've got from our rhesus airway. These were cultured on transwells. We've got some of our NHP gut organoids, and then we've got some just IF confirmation of the NHP cilia when they've been cultured as a monolayer. So just to summarise, I have persuaded you that MPSs are an important tool in this drive to reduce animal use in scientific research. We're using the emulate model, and we've established both the airway and the alveolar model, and we've got bespoke solutions for using these at high containment. We've demonstrated robust infections with 3 of the pandemic human coronaviruses, and we've put medical countermeasures in to show effective inhibition. So we hope that these models are going to help us best be prepared for future pandemics by having human relevant models ready to go. But we're also working towards NHP chips as part of this solution, as I mentioned, to bridge the gap between the regulatory data that's already existing and the new data that's going to come out from these human organ chip data. So that just leaves me to thank all of my team at UK-ICN, our collaborators at Liverpool and QIB, and of course our funders at FDA. I'm happy to take any questions.
So do you have some time for questions now? Maybe I can start. I was wondering about the lung on a chip model that you have, just about the sort of 3-dimensional depth of the cells. I mean, how thick does that slice or how thick does the sort of tissue get on that?
So they can get several layers thick, especially the airway models. With the cilia, they can get quite thick and they generate mucus. So we haven't been able to access the membranes within the chips, do kind of cross sections and see the thickness by kind of pathology staining. But I know from doing, we sent some of our chips off to test. We put them on her lovely confocal, and there's several layers deep, so it's quite challenging to kind of look at the different layers on a standard microscope. So the confocal's been great for kind of isolating the different layers.
And the alveolar ones, they're presumably much thinner then?
Yeah, they're much thinner, but they've got the endothelial cells underneath,
okay.
So you've got the more complex kind of system.
David?
It's maybe more of a future-looking question. And these models are like really hard to work with, but you get something that's much more relevant. But for drug screening and everything else, sort of speed. Where do you see for SARS-CoV-2 is later, but where would you see the niche being? Is it you come in after a drug screen, but before a preclinical model? Do you come in after the preclinical model and you're doing human-like?
So yeah, a bit of both. So other companies have kind of developed, especially with the tox, as you say, they've got kind of liver chips, which are high throughput. And they're already using these as screening to test which drugs to take forward. But also then you can use them at a less high throughput, but there's companies that are developing these that you can do. They're running alongside clinical trials to reduce the number of animals. So they're doing a lot of the kind of dose testing in chips before going into animals. So kind of already reducing the number of animals. So yeah, at the moment it's being used mainly to reduce the number of animals used in that kind of preclinical stage. But I know going forwards, it's hoped to be able to replace animals completely.
Okay, thank you.